In this video, we're going to look at how electrons are arranged in the modern model of the atom and how this differs with the model that you would have used when you were doing GCSE. We'll look at shells, subshells and orbitals and different ways that you can display this information. In the next video, we'll look at why this is important and how it can be used to explain certain data. So by the time you finish GCSE chemistry, you are probably very familiar with this model of the atom. We've got a central nucleus and then we've got electrons orbiting around the outside. And those electrons are at fixed distances, moving around orbits that we call shells. And you probably would have learned that it was really important that when you were drawing an atom, you started with the first shell, with the inside shell, and you only moved outside when that inside shell was completely full. And you might have also been told that the first shell had room for 2 electrons, the second shell had room for 8, the third shell had room for 8. Now, a lot of that has some basis in reality, and it's a really useful starting point for us talking about atomic chemistry, but it's largely been simplified, and so there are some of those ideas that you're going to need to let go of before we go any further. So firstly, this idea that electrons are these tiny solid particles, and if you had a small enough pair of tweezers you could just grab one. Well, that's not really how we think about electrons now. We think about electrons as clouds of charge that probably occupy a particular space. So we can say, oh, if I was looking in an atom, there's 90% chance that I would find some charge density here. So we're not sort of thinking about a tiny solid thing we could grab so much as a sort of smear of charge. The second simplification is this idea that if I have a particular electron and say it's in the second shell, it will just stay there, continually orbiting at the same distance forever and a day. But we actually know that if we give an electron some more energy, then it's capable of moving to a different shell, to a different energy level. And this is what's responsible for those characteristic colours that are given out when you do flame tests. It's all about electrons moving around and releasing energy and releasing light of a particular wavelength. Next on the list of things that we oversimplified at GCSE are 2 linked concepts. So at GCSE, when you were drawing diagrams of atoms, you knew that you had to start on the inside and work your way out, and you knew that you couldn't move on to a new shell until you finished the shell that you're currently in. Now, there is some truth in this, but the problem is that as the shells get bigger and bigger, we start breaking them up into subshells. So the real rule is not that you can't start a new shell until you finish the shell you're in, but that you can't start a new subshell until you've finished the subshell you're in. Now, when you're starting out with atomic chemistry, this distinction doesn't really matter. Your first shell only has one subshell, so the shell and the subshell become full at the same point. It gets more complicated when we get to the bigger shells, and when we start having a situation where the first subshell of the next shell requires less energy to fill than the last subshell of the shell you're currently in. Don't worry, this sounds complicated, but we are going to go through it in loads of detail. But so what you have to bear in mind is that we're going to stop using that rule that I can't start filling shell 4 until shell 3 is full. Okay, because the first subshell of shell 4 is going to be easier for us to fill. So instead of having this system where we start in the middle and we constantly work our way out, we're now going to have a system where we bounce out to the next shell and then we come back again. The final point on our slightly too simple at GCSE list is about the number of electrons that fit in shells, and this links back with this idea about the fact that we couldn't start filling a new shell until we'd filled up the shell that we're in. So at GCSE, when you were drawing atoms, you would have drawn one shell for hydrogen and helium, and then a second shell which took you up to neon, and a third shell that took you up to argon. And at that point, that third shell had 8 electrons in it. And then you started the fourth shell. So of course, you finished GCSE with the idea in your head that you can only fit 8 electrons in shell 3. And that's not true. What is true is that you only put 8 electrons in shell 3 before you start filling shell 4. You then turn around and come back to shell 3, but because at GCSE we only draw atoms up to the size of calcium, we never encounter that. So just bear that one in mind, we can fit more than 8 electrons into the third shell. So how many electrons can you fit in a shell? Well, there's a very simple rule, which is 2n squared, although it may just be easier to remember the numbers themselves. You already know 1 squared is 1 times 2 is 2. There is room for 2 electrons in the first shell, and then 2 squared is 4, 4 times 2 is 8, 8 electrons in the second shell. Following this same rule, we find out that actually the third shell has room for 18 electrons. You may also hear those shells being referred to as energy levels, and as we mentioned in the introduction, each one of those shells can be divided into one or more subshells. Each of those subshells has a name, S, P, D and F, so I tend to remember PDF as in printable document format, the thing you open with Adobe, and each one of them has a particular number of electrons they can hold, 2, 6, 10 and 14. Those sound like random numbers, but if you think of them, they're all double and odd numbers. So your odd numbers are 1, 3, 5, 7, and then your number of electrons in each subshell are double that. Shell 1 only contains an S subshell, so it only has room for 2 electrons. And then with each new shell, we're adding a new subshell. So shell 2 has the S subshell, but it also has the P subshell. And then shell 3 has S and P and D, and shell 4 has S, P, D and F. Although you don't really need to worry about F in the same way that at GCSE we only went up to calcium. For A level, we're only going to go up to an atomic number of 36, so you don't actually need your F subshell. You just kind of need to be aware that it exists. Now, if we look at our periodic table, we can start to divide this up based on what's the subshell that these elements have their final electrons in. So if you're an element where your last electron goes into the S subshell, then you're part of the S block. If it goes in the P subshell, then you're in the P block. And if it goes in a D subshell, you're in a D block. An incredibly common 1 or 2 mark question at the start of any of the A-level chemistry papers is asking you to write out the electron configuration of an atom or 2 atoms or an atom and an ion. So this is really, really straightforward. If we start off with hydrogen, we write a big 1 for the first shell, an S to show we're talking about the S subshell, and then a superscript 1 to show that the first S subshell has a single electron in it. Then for helium, we've obviously got 2 electrons in that subshell, so it becomes 1s2. For lithium, we've got that full S subshell, so 1s2, and then we've moved on to the second S subshell, so we go 2s1, and this continues, so we have 2s2. Then, because we're in the second shell, we now have access to a P subshell. So for boron, we have 1s2, 2s2, 2p1, and then we carry on going like this, so we have 2p2 for carbon, 2p3 for nitrogen, 2p4 for oxygen, 2p5 for fluorine, and 2p6 for neon. So you can see that certainly to start with, this is very straightforward. Pause the video at this point and just have a quick check to make sure that you can do these 5. Hopefully that wasn't too tricky and you've managed to correctly identify that for each one of these you should be adding 1 more electron, so we have 3s1, 3s2, 3p1, 3p2 and 3p3. I don't think I've ever seen an exam question which asked you to give your answer in noble gas nomenclature because, to be honest, that would be too easy, but sometimes they will use it and expect you to understand what it means. So the idea behind noble gas nomenclature is that because we know that we have to fill these subshells in a particular order and that we're not going to have moved on before one is full, once you get to a certain point, you know that all the inside shells are full. So it would kind of just be easier to just miss out writing them, but we don't want to imply that they're not there. So what we do instead is we use the symbol of the noble gas that has those full shells, and we just kind of put that in instead. Now, you can see here, using helium is kind of silly because writing 1s2 and writing helium take about the same amount of time. But you can imagine once you get onto much bigger elements and you can use neon or argon or xenon, this is going to save you a lot of time. So for each one of these, you can see you can take out 1s2, 2s2, 2p6, and instead just write in square brackets neon. Where you get these questions ask you to write out the full electron configuration of an atom. It's fairly typical that you'll be asked to do 1 atom and then also 1 ion, so you need to be prepared for that. I'd really strongly recommend that when you meet one of these questions, you write out the full electron configuration of the atom first and then look at how you need to edit that to do the ion. If you do it in just one step, it's really easy to make silly mistakes. So take, for instance, this lithium here. I know that the atom would have an electron configuration of 1s2, 2s1. And then to make the lithium positive ion, I need to lose a single electron. So just like you did at GCSE, where you started on the outside and worked your way in, I'm going to take that electron out of the 2s subshell. So my final answer would just be 1s2. Likewise for beryllium, I start out with 1s2, 2s2, and then I need to lose 2 electrons, so I take them out of the 2s subshell. For oxygen and fluorine, they're forming negative ions, and that means they need to gain electrons, and they're basically going to gain electrons until their 2p subshell is full. So for each example, we end up with 2p6. Now this all works beautifully and straightforwardly until we get to shell 3, and this is where it starts to get complicated and there are some extra rules you need to be familiar with. So shell 3 can contain 18 electrons, and it's made up of S, P and D subshells. So the S and the P subshells you've already met, you already know how they work. Here's the thing, the D subshell is higher energy than the 4S subshell. So you know how we said at GCSE we couldn't start a new shell until we'd filled up the previous one, but now we're saying we can't start a new subshell until we filled up the previous subshell. So we get to the end of 3p, and you would expect that we would go on to 3d, but instead we're going to go out to the 4th subshell, and then when that S subshell of the 4th shell is full, we're going to come back and fill in 3d. So as an example of this, potassium has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and then it's not 3d1, it's 4s1. This makes a bit more sense if we show you a picture which actually shows the position of the different electron shells in terms of how much energy they require. So you can see here, if you look on the left hand side, we have the S subshells, and if you find 4s, it's higher than 3p, but it's lower than 3d. And so this means we're going to fill it up first. So again, as an example, if we take scandium, we have 1s2, 2s2, 2p6, 3s2, 3p6, and then before we get to 3d, we have 4s2 and then 3d1. Now it doesn't matter whether you are more comfortable writing them in this order because they get filled in this order, or if you're more comfortable writing them so that all the 3's are together and then the 4's. It's fine to do it either way, you're not going to lose any credit. Each one of these little lines in this picture represents 2 electrons, but don't worry, we're going to get to them in a minute. Now that you've got your head around the idea that we're going to fill 4s first, there's one more thing. We fill it up first, but we also empty it first. So if we have an example like the scandium that we just saw, we fill up that 4s subshell before we get started on the 3d subshell. But then when scandium forms a single positively charged ion, we don't take out the 3d electron that we put in at the end. We take one out of the 4s subshell instead. So 4s fills first and it empties first. And that's also true of higher shells. So when you get to 4d, you fill 5s before you fill 4d. One more rule. So atoms gain additional stability from having either 5 electrons or 10 electrons in their d subshell. So if you end up in a situation where they almost do, as in where they have 4 or they have 9, at that point an electron moves from the 4s subshell to the 3d subshell. So the classic examples that you want to be aware of are chromium and copper. So if we just look at some transition metals here, if you look at vanadium, which comes just before chromium, vanadium has 4s2 then 3d3, because as we keep saying, we're going to fill the 4s before we fill the 3d. And so we would expect that chromium would also have 4s2 and then would have 3d4. But instead of that, we go down to 4s1, and the extra electron allows the 3d subshell to now have 5 electrons in it instead. Let's now have a look at some example questions from some recent exams. Pause the video and see if you can work out what the answer to each of these is. First up, we have calcium, nice and straightforward. 1s2, 2s2, 2p6, 3s2, 3p6, and then the only thing we have to remember is that we're going to fill the 4s subshell before 3d, so we finish off here with 4s2. Aluminium is also very straightforward, nothing complicated here. Then we move on to chromium, and as I mentioned before, I would really strongly suggest that you start out writing out the electron configuration of the atom and then look at what you need to do to change that into an ion. So already chromium is a little bit complicated because remember we have that rule where an atom is at its most stable where it's got 5 or 10 electrons in the d subshell. So we start out 1s2, 2s2, 2p6, 3s2, 3p6, nothing complicated yet. We remember to fill 4s first, but because it's chromium we end up going 4s1, 3d5 instead of 4s2, 3d4, which would be less stable. Now we've got to consider what we're going to do to turn it into a chromium ion. So we're going to lose that one electron that was in the 4s subshell. So that's a single electron we've lost, but we now need to lose 2 more, and they are going to come out of the 3d subshell. So we end up with 3d3 at the end. Likewise, with chlorine, I'd suggest you start out thinking about the atom and then look at what you need to do to edit it. So the atom would be 1s2, 2s2, 2p6, 3s2, 3p5. Then we need to gain an electron to give the ion its negative charge. And so we get 3p6. For iron, the atom would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, because remember we're filling the 4s subshell before the 3d subshell, and 3d6. However, this is an ion, it's a 2+ ion, so it needs to lose 2 electrons. And remember we're going to lose those 2 electrons from the 4s subshell before the 3d subshell. It fills first, but it also empties first. So we remove that from our electron configuration. Now this is a slightly different question, but it requires you to be aware of the same skills. So we've got an element that forms a sulfate with the formula QSO4. Hopefully from GCSE you're aware that an SO4 compound ion has a charge of 2-, and therefore whatever is forming an overall compound with it must have a charge of 2+. So we're looking at these different electron configurations and we're looking for something that could form a 2+ ion. In each instance they've used the noble gas configuration, they've put neon in there, so we're just looking at our 3s and our 3p subshells. So if something has 3s1 as its last electron, when it comes to form ions, it's going to lose that one electron, okay? It's going to form an ion that has a single positive charge. If it's finishing with 3s2, then it will form a 2+ charge. 3s2, 3p1 would be aluminium, and so it's going to form ions with a 3+ charge. And 3s1, 3p2 just doesn't exist. So our answer to this question would be B. Finally, in this section, we need to divide our subshells into orbitals. So we mentioned at the start that we no longer think of electrons as sort of physical particles that we can grab, we think about them as a cloud of negative charge. And so the space that that negative charge fills up, that volume, is called its atomic orbital. Now, each orbital has room for 2 electrons, but as we know, all electrons are negatively charged, and therefore all electrons are trying to repel each other. And so you're not going to completely fill an orbital before moving on. In fact, you're going to do the opposite. You're going to put 1 electron in every orbital that's available to you, and then and only then are you going to go back and start pairing them up. And this is going to help us to explain some data about something called first ionization enthalpy, which is basically how easy or hard is it, how much energy does it require to remove electrons from atoms to make single positively charged ions. You know that an orbital has room for 2 electrons, so just pause the video quickly and write down for me how many orbitals are there in shell 1, shell 2 and shell 3. Hopefully you managed this okay. Shell 1 has room for 2 electrons, remember, so therefore it has room for 1 orbital. Shell 2 has room for 4 orbitals, that's 1 s orbital and 3 p orbitals. And shell 3 has room for 9 orbitals, 1 s orbital, 3 p orbitals, and then 5 d orbitals. These orbitals have characteristic shapes. So we talk about the s orbitals as being shaped like a sphere, and then the p orbitals are shaped, sometimes they say like dumbbells, but basically like this. And then when you get to your d orbitals, they kind of look a little bit like butterflies. You're not going to be expected to be able to draw these, you just need to recognise what they are. Finally, we're going to look at one way that we can represent this graphically. You'll also see pictures where you have a long horizontal row of boxes and you fill them in exactly the same way. We're using arrows to represent electrons, and the arrows are going to point up and down to demonstrate that they represent electrons with opposite spin. You need to remember that in each instance, we're going to work from lowest energy to highest energy. We're never going to start a new subshell before the previous one is finished. And then within a subshell, we're going to put one electron into each orbital before we go back and start pairing any of them. So if we work from the very beginning, if we start with hydrogen, hydrogen has one electron, so we put it into the first subshell, into the first orbital. And then when we get to helium, we have a second one. Well, there aren't any more orbitals in the same energy level. So we're just going to pair those electrons there. So you can see we've got one arrow pointing up, one arrow pointing down. Then for lithium, we move on to the 2s orbital. And so we put one electron in there. And then again, there isn't another orbital at the same energy level. So we pair the electrons. Now we've moved on to our 2p subshell, and now we have multiple orbitals with the same energy level. So we're going to put one electron in each of these before we start pairing anything. So for carbon, we're going to have two unpaired electrons in two separate p orbitals. Once each of those orbitals is full, then we need to start pairing. So we've covered shells, subshells and orbitals, full electron configuration, noble gas notation, and also how we can draw this graphically. I hope this was helpful. Don't forget to subscribe.